Professor Jeff Wilkerson here with an introduction to exercise 4 from Astronomers as Observers and Experimenters Laboratory Manual in Astronomy, published by Kindle Hunt. So what we're talking about here is extinction of light by the atmosphere, really scattering out of light by the atmosphere. And this is an interesting exercise for a number of reasons. And what you're given is a bunch of data. It is real data. It's data that I've taken here with my research students as we have a project that we've been studying the same group of stars for over 20 years now. And so this is actual data of stars rising into the atmosphere. And what happens is the stars get higher in the atmosphere, they come through less and less and less atmosphere. And so as that starlight passes through the atmosphere, light's getting scattered out. And as light gets scattered out, the atmosphere, the starlight looks fainter and fainter and fainter and fainter to you as it gets there. So the star should look fainter here as it's coming through more atmosphere than it does here as it's coming through less atmosphere. And so this is what we're looking at. So we are measuring the brightness of the stars over a relatively limited range of altitude over a relatively limited time. Now you got all kinds of other problems that we didn't deal with here that say that the water vapor in the atmosphere may be changing, other things may be changing, so it may not just be the star rising into the sky that causes the star to appear brighter, or the star setting down lower in the sky that causes it to appear fainter. There may be other things going on. In fact, because we were doing aperture photometry here, where we were drawing a circle around the star and adding up all the light that was inside that circle, because of that, if the seeing was changing, if the atmosphere was becoming more turbulent or less turbulent and the size of the star was changing, that could actually change the normalizing that we needed to do. But that's the key fact here. The key idea is that we have to normalize out this changing brightness of the stars. We have to work on it pretty hard. I tell my research students all the time that working on a research project like this is a lot like writing poetry. You're after some big idea. You're really trying to do something big and tackle something there that touches truth or beauty or whatever it is you want to be doing. But how you sweat the details, how you take care of issues like this, determines whether you get the job done to your satisfaction or not. In fact, I would say it's likely that most research projects hinge on whether or not we can take care of this kind of business, whether we can do this kind of normalization and this kind of practice at taking care of the data set, at getting the data set in shape to measure what we want to measure. So this is real science right at its core to try to figure this out. And so we have to normalize this out. Now, what's built into this exercise is the idea. You know, the sky is blue. The sky looks blue to you because when you look at the sky, you're seeing sunlight without looking directly at the sun. The sun's over here, but you're looking over here, and you're seeing the sunlight that's being scattered down to you from the atmosphere. Looks blue because blue light gets scattered preferentially to red light. So that means that bluer stars should be affected by this atmosphere more. They have light that's more prone to scattering. And so we would expect to see this needing to correct for atmospheric extinction to be greater in the bluer stars. This is a real problem, again, as we're trying to dot all the I's and cross all the T's and take care of all of the details. The fact that we have, in our case, 1,600 stars that we're observing all the time, all night long, and they're all different colors. And they got sometimes we know those colors well, and sometimes we don't, all kinds of things going on. But in any event, we might expect to see a difference between red stars and blue stars, so we give you that information. We give you color indices so you can see the redder stars, you can see the bluer stars, and you can see if the way we're going to try to get at that is if we plot the brightness of the star as a function of time. Does the slope of that? So here's an interesting thing to keep in mind. So we're plotting the signal, just straight up signal, as a function of time. As the star rises into the sky, you see it getting brighter. Pretty dramatic, actually, that you see right there And so it's kind of great to see that it's not moving very much, a few degrees of altitude. It's getting a few degrees higher in the sky, and you see a pretty dramatic change. So what we're doing is we're fitting a line to this and measuring the slope of that line and using the slope of that line. The steeper the slope of the line, the greater the effect of the atmosphere is what we're saying here. And so this is great, and this is a good way to do this. But oh my goodness, be careful about this. I spend such a large fraction of my life that, that trying to explain to people, trying to warn students, trying to warn anybody, stopping people on the street and trying to warn them about treating data as linearly related, two variables as linearly related when they may not be and probably aren't, and in fact aren't in this case, linearly related. We would not expect the signal versus altitude to be linearly related in this way. And so acting like it's linearly related is problematic and can cause us all kinds of problems, and we just don't want to do it. So here we are asking you to do it, which is keep that in mind. So we're not trying, first of all, we're not trying to find a model of a big model to say this is mathematically, genuinely how signal depends on altitude. We're just trying to find a convenient way to compare one star to another star to another star to another star. And this turns out to be a relatively convenient way to do this, even though the linear fit is probably not appropriate. And we know it's not appropriate for any of these stars. At least it's the same thing for each of these stars. And it's a relatively simple thing. It's a quick and simple thing for us to do. If we were wanting to do this more seriously, we would find a different fit to do that there, and we could do that, but it's not appropriate for this setting, for this particular exercise. So we're going to do that linear fit. Now, another thing to keep in mind is over a small enough range, which this is a pretty narrow range of altitudes, no matter what the shape of this function is, we can maybe get away with fitting a line okay. This probably looks something like that, right? And if we tried to fit a line to that whole range, where this is a bigger altitude range across here. Now, so this is 5 times the altitude range, or 3 times the altitude range of what we had right here. And we see that curvature in the line just doesn't work very well at all. But if we confine ourselves to a narrow range like that, then we get a much better approximation of the data by fitting the line. And that's a key point too. We're just trying to get an approximation of the data. We're not trying to find a model of physical reality that explains exactly how this changes. We're just trying to find something that works for us. We call this an empirical fit to the data. This isn't based on a model. This isn't trying to come up with some idea of how light is scattered in the atmosphere. It's just a straight up empirical fit of signal to altitude and saying, is the linear fit good enough for us to check the slopes and compare the slopes from one to the other? So keep that in mind as you go through there. What you're doing is comparing the slopes of these fits, even though these data probably aren't linearly related, but over a narrow enough range you can get away with it. Astronomers actually do that quite a bit. They usually don't fit lines, but you can have all kinds of data that are related one to the other. So you might have an exponential relationship between data on your y-axis and on your x-axis, and over a small enough range, you get away with fitting a polynomial, a power law. Power law is typically what you would fit. You would say, y is equal to some constant times x to the n, where n is the power in the power law. In this case, we're just using n to be 1 to make that a line. So anyway, that's just a word of warning for you, but really a great exercise to see the dramatic effect that the atmosphere has on the signal that's being measured, and how that signal, that effect, it depends on the color of the star. Pretty quick and easy way to figuring out something that's important and we have to deal with every single time we go about doing an astronomy observation, an astronomy experiment. So good luck with the exercise. I hope you find it enjoyable. I hope you thinking about it in this way helps you to appreciate the importance of what's going on. Take care, everyone.